Today's going to be a little different. Today is going to be maybe the most philosophical lecture of the entire semester. We're going to talk about how proofs and programs are so intimately related that, in fact, if you look at them right, they're really just the same thing. We've been doing proofs about programs. Today, I want to talk about the fact that proofs are programs, when you look at them in the right light. And I want to preface this by saying, I've been where you are. I've been through a lot of lectures in my life. There are very few lectures I remember clearly from 20 years ago. The day I learned this material was a watershed day for me. I remember that lecture clearly. It is one of the things that made me want to do what I am doing right now, because it is just one of the most beautiful results I know of in computer science. I hope you feel some modicum of that excitement by the time we're done here today, as I did when I first heard this material about 20 years ago. This is a lecture in 3 acts. Act 1, types are propositions. I'm going to start off by giving you 3 functions. They look really simple at first. So these 3 functions I'm calling apply, const, and subst. Apply, hopefully the name makes some sense right away when you look at this function. It's taking its argument f and applying it to its other argument x, right? Just f applied to x. Just function application. Super simple function. Const, its name is meant to suggest also something reasonable. It's the constant function that always returns x. So const of x gives you back an anonymous function. That anonymous function ignores its input. It does nothing with it. And then just returns x. So anytime you call const of x after that, it's going to give you back that value x. It's constant in that sense. Finally, this function subst, which takes in 3 arguments, it's a little more subtle. This is not necessarily something that you would come up with right away on your own. But let me remind you of how substitution worked. So suppose you had, an expression E1 applied to an expression E2 in the substitution model. And suppose that you were going to take that and you were going to substitute something in there. Right? Suppose you were going to take, some value v and substitute it for the variable x. Well, the way you did that is by kind of pushing that substitution down into the individual pieces. So that would actually end up being E1 with v substituted for x applied to E2 with v substituted for x. All right. This function subst is doing something kind of similar. Think of x and y as corresponding to E1 and E2. And think of z as being like some kind of information being done about the substitution, like what substitution is occurring. Then what this is saying is this function is going to kind of push that down. It's going to take x and z together and y and z together, just like this does E1 with that substitution and E2 with that substitution. Okay, 3 innocent-looking functions. Let's look at the types of them. Types are very important to what we're about to do. So the type of apply, it takes in a function, and we don't know anything about that function, or its input type or its output type, so that's just alpha arrow beta. But since f is being applied to the second argument x, the type of x has got to agree with the input type of f, so x is going to have to be of type alpha. And then after doing that application, of course, you're going to get back a value of type beta. So that's the type of that function. The constant function, well, it's going to take in an argument x. We don't know anything about its type, so let that be alpha. The anonymous function that gets returned by const, we're not even going to use the input there, so that's totally unconstrained. That could just be beta. And then it's going to return alpha, because it's always going to return that original input. Type of subst, a bit more complicated. So if you work through what all of the types have to be here, and that actually would be a good exam problem at some point. If you had x, y, z, well, x here is going to be a function, and it's going to take in an argument and another argument, so that's alpha, arrow beta, arrow gamma for x. That second argument, y, itself must be a function, because y is being applied to something there. And that third argument, z, let's start by saying that's alpha. Well, if z is alpha, Then y being applied to z, y has got to take in an alpha. We don't know what it gives back. Let that be beta. And therefore, x is going to take in an alpha, which is what we said z is, a beta, which is what y returns, and give us back a value gamma. We don't know anything about that value. Okay. So those are the types of those three functions. And now suppose I erase the functions, leaving just the types. All right, so just sort of like, okay, if you had goggles to put on, right? Suppose we had given you some like rose-colored goggles to put on so that you couldn't see the print that was in that color before. Then all you'd be able to see that's left here is the types. So I want you to put those goggles on, and we're going to do that several times throughout this lecture. But furthermore, I want these goggles that you're imaginarily putting on to have another special property. They actually change what you see in terms of the symbols. So instead of these function arrows, and instead of these alpha and beta, here's what your goggles should do. They should replace the function arrows with an implication symbol. How many of you are familiar with that implication symbol? Okay. Many of you, not necessarily all. So in logic, sometimes when we have an expression like P implies Q, we might write it in English that way. In formal logic, when we're writing things down just with symbols, there are various symbols that can be used. This is one of them. P implies Q. It's written as a kind of double right arrow that way. People use all other kinds of symbols for that too, but this is a common one. Once you make that change of symbols, those types look less like types and more like logical propositions, logical formulas that you could attempt to prove. In fact, let's even get rid of alpha and beta. Let's just replace them with A and B. So now you've got these three logical formulas. The first one says A implies B implies A implies B, and so forth. Const, the one for it, says A implies B implies A. This is maybe the easiest one to wrap your head around. Suppose A here is a proposition meaning that it's nice outside, which it is today. Suppose B is a proposition that means, I don't know, you had an egg sandwich for breakfast. Well, that's sort of irrelevant. If it's nice outside, then it's still nice outside. So from it's nice outside implying you had an egg sandwich for breakfast, you can still conclude it's nice outside. So that's how to read these sorts of logical propositions here. Okay. I'm going to put one more set of parentheses around it just to make clear how we parse this, because if you're not used to these symbols, maybe it's a little unclear how to do that. Right, so we've got parentheses around these. Implication normally associates to the right, just like function arrows do. Okay, so now we've got these like fully parenthesized. Totally, they are propositions now. They don't look like types exactly at all anymore. And now the question is, do any of you recognize these propositions? Because it is possible that some of you will have seen them somewhere before. Not necessarily all. Did anyone have Professor Halpern in discrete math? Some of you? Yeah, not a whole lot of people. He used to teach it more regularly. I'm going to show you a slide from his 2800 course. Again, this was a long time ago. It was 2016 fall. But this is a slide he had in that course that semester when he covered logic. Consider the following axiom schemes. Okay, let's leave alone what that means for now. But look at this first one here. A implies B implies A. Look at the second one. A implies B implies C implies A implies B implies A implies C. Well, if we flip back, that's actually exactly what we had here. And the other one is, let's say A1 up here. That's exactly what we had here. Okay, so why did he have this slide? Well, I'm not going to go into all the details of logic here, but he was teaching people how to use logic to reason. And when you use logic to reason, you have things called axioms. Axioms are formulas that you're allowed to always use as valid ways to do reasoning. So it's always valid to conclude that A implies B implies A, no matter how you instantiate those kind of propositions A and B that are sitting there. Those are called atomic propositions. Atomic as in like indivisible basic building blocks. Okay, so he gave these axioms here Because when you want to reason, when you want to do proofs with logic, you're always concerned about, are my proofs right? Right? So there's something that's like true out there in the real world. I'd like to be able to prove that it's true, and I'd like to make sure that any proofs that I do never inadvertently let me prove false things. Correspondingly, if there are true things out there in the real world, I'd like to be able to prove all of them. Like, I don't want a kind of miserable, poor little logic that only lets me prove certain things. I want to be able to prove as many things that are true as possible. All of them, in fact. Those two properties, they're sitting up here. They're called soundness and completeness. Sound means you can only prove true things. Complete means you can prove all the true things. It turns out he gave these axioms because they are sufficient. They are sound and complete. They are exactly what you need to do like perfect logical reasoning. Okay, so you actually need A3 as well. We haven't talked about that one. And there's one other thing you need too, which is called modus ponens. This is a Latin phrase that goes along with another principle of reasoning. Here it is. Modus ponens says that if you can conclude A implies B, and if you can separately conclude A, then from that you're allowed to conclude B. Right, this is a basic principle of reasoning that says, for example, if you walk outside in Ithaca in January and it's cold, then you're going to need a coat. Well, suppose you walk outside in Ithaca in January and it's cold. Then you're going to need a coat. Like, this is just basically how we reason. This has been known since the ancient Greeks as a principle of reasoning. Okay, going back to our three formulas, we have A1, A2, and here we have modus ponens. I'm not writing it as a proof rule as we did up here. We've seen proof rules for type systems before in this class. Instead, I'm writing it kind of as an axiom. If you have A implies B, and you have A, then you can conclude B. Okay, so there was a lot of logic there. Let's come back to the programming aspect of it. What have we learned from doing this little exercise of putting our goggles on and looking at these programs and their types in a particular way? What we've seen is that logical propositions, things that you would do in a logic class, in a math class, not necessarily at all in a computer programming class, actually can be read as program types and vice versa. There's this correspondence going on between them. Anywhere you see a type variable in a program type, you can also think of that as an atomic proposition in a logical formula. Anywhere you see a function type arrow showing up in the type of a program, you can read that as an implication. And you get logical propositions out of program types and program types out of logical propositions this way. Okay, so maybe that was an accident, if you're going to be a skeptic about this. All I did it for was implication and just atomic propositions, right? There's all kinds of other things in logic, like disjunction, conjunction, negation. That would be not and an or, right? You can actually do all of those as well. So let's do just an exercise here on conjunction and truth. Here are some simple programs. We wrote these a long time ago, first and second, right? These take in a pair and give back either the first component of the pair or the second component of the pair. Here's a function that actually creates a pair. So you give it two values, A and B, and it just pairs them up together. And finally, here's the unit value of unit type. We'll come back to why I named it TT in a second. Okay, I've given all the types here. First takes an alpha star beta, a pair of an alpha and a beta, gives you back an alpha. Second gives you back the corresponding second portion of the pair, so beta. And the pair function here takes in, let's say A is of type alpha, B is of type beta. It gives you back something of type alpha star beta. It just pairs them up. All right. Put on those hypothetical goggles again. It causes you to ignore the programs and just look at their types, and furthermore to reread those types as logical propositions. So we've replaced star everywhere here with conjunction. So before we had alpha star beta, now we've got A and B. So think of star and conjunction as being what your goggles cause you to see when you take them on or off. So we've got A and B implies A and B implies B, A implies B implies A and B, and we've got simply true for the last one. your goggles are going to cause you to read unit as true. Okay. Well, look at those formulas. Not only are they formulas that make sense as logical propositions, in fact, those are all true formulas. If you know that you have 3110 taking place in Bailey Hall, and if you also know that your next class is, I don't know, in Malott or something like that, then you certainly know that you have 3110 in Bailey Hall. You're allowed to forget about that second piece of information. Same thing happens here. You're allowed to forget about that first piece of information. It's still a valid way of doing logical reasoning. Similarly, if you can assume A, if you can also assume B, then together those are sufficient to establish the truth of A and B. So it's not just that we can read these types as logical propositions, it's that the types we read turn out to be true propositions. They actually are. That was exciting. Somehow I feel like that made sense at a meta level. Because we're looking really deep down the rabbit hole there. Okay. It's that we can see that these types really are true propositions. They are things that should be concluded from the principles of logical reasoning that we've established as humans over the last couple thousand years. So now I can expand our table of types and propositions. Not only do we read type variables, function types as logical propositions, we can take the product type asterisk and read that as conjunction, which in logic is written with that kind of and symbol, that kind of wedge-shaped symbol. And if you want, you can read the unit value as true. Why is that? Well, think of it this way. What is a type? Well, some people would say it's a set of values, and maybe some operations on those, but let's focus on the set of values for the moment. A type could have many values. Bool has 2. Int has 2 to the, well, it depends on exactly the implementation, maybe 2 to the 64, maybe 2 to the 32. OCaml, it's actually 2 to the 31 or 2 to the 63, depending on what your underlying implementation is. Unit, there's only one value of that type. Could there be a type with no values? Could you define a type that has no values in OCaml? Yeah. Couldn't quite hear you, just speak up real loud. Void. OCaml doesn't have a built-in type called void. But it turns out you can create it yourself. So this is something you would never expect to see necessarily. You would not have guessed that this is possible. But I can say type, you called it void, I like the name void, I'll call it that, equals vertical bar. I'm defining a variant here that has no constructors at all. Double semicolon to finish that. So that's really weird looking syntax, right? It just means that there's no constructors for this type at all. And now, how would I construct a value of type void? Well, it has no constructors, so I can't write down any value of type void. So another name for this type, if I didn't want to call it void, by which you should think of void there as meaning like devoid of having any values. You could also call it empty, because that type it's an empty set when you look at it as a set of values. Okay. So, empty there has no values. What does unit have? Back to that. Unit has one value. It's always guaranteed to be there, just like true is always guaranteed to be true, as it were. It's always something provable. So that's why we think of unit as corresponding to true. And by the way, false would correspond to that empty type, to that void type. Okay. So I've done this now for implication, for conjunction, for true. We actually already did it for false just now. You can also do it for disjunction and negation. I'm not going to do it here because we don't have quite enough time to go through it. It is in the notes, so you can take a look at it there. All of these logical propositions can be read as, all of these program types can be read as logical propositions and vice versa. And when you write down programs that have these types, we have seen examples now, and I will tell you it's just true in general. They always turn out to be provable propositions, things that are in fact true. So every time you wrote down a program that the OCaml compiler accepted as being well typed, you were actually at the same time writing down a true logical formula. So we can say that program types and logical propositions are fundamentally the same idea. But that's not all. It goes deeper. So, Act 2. Programs are proofs. Back in lecture 19, we talked about type systems. So let me remind you a little bit of what we said about type systems. We had static environments. A static environment was a map from identifiers to types. And we had a typing relation. It was a ternary relation. We wrote it this way. Env proves E has type T, or env shows that E has type T. And that's true as long as E does indeed have that type T in that static environment. And we gave a bunch of rules for concluding when that relation holds. Here's a rule for function application. So if in an environment you can show that E1 is a function type that has a type T arrow U for some T and U. And if you can also show in that same static environment, all the same variables are in scope, that E2 has type T, then that environment allows you to show that E1 applied to E2. So take that function E1, run it with input E2, which does have a matching type T there. Those are the same. What is the resulting type of that going to be? Well, it's going to be U, of course, because that's the output type of that function. So let's just put that typing rule by itself here on the slide. And I'm going to color code pieces of it, as we've been doing a little bit so far. I'm going to color code the program and the type. And now I'm going to ask you to put on your goggles once more. And when you put on those goggles, you're going to be left with these types. If T arrow U and T, then U. Well, of course, your goggles also are going to cause you to reread that function arrow as an implication. And now my question, hopefully more of you will say yes this time. Do you recognize this rule in logic? I see heads shaking. You do. I've even had it on the slide so far today. This is just modus ponens. This is that principle of reasoning that says when you have A implies B and you have A, you're allowed to conclude that B holds. Or from the assumption of A, if you can conclude B, then if you do indeed have A, then that suffices as an assumption to be able to conclude B at that point. So modus ponens, it turns out, with our goggles on, actually corresponds to this typing rule for function application. And that is deeply surprising. You would never have expected that necessarily to happen at first. Okay. We're going to dive deeper into this. But to do it, I need to take a little bit of an intermission and do some more logic that you might not have seen before. Just a little logic here. Okay, we've been talking about things that are provable. A logical proof system is a set of rules and axioms that together say, here are the ways I am formally allowed to reason in logic. A lot of the times we're a little bit uncareful with this. We're not necessarily rigorous about it. We just do our proofs in English. But you can also write down proofs completely just using logical formulas and symbols. And that's kind of similar to how some languages are untyped versus typed. Right? So in some languages, like Python maybe, you're allowed to write down expressions that don't necessarily make sense when you think about them from a typed perspective, but OCaml insists that all the symbols that you write down make sense together, right? And because it runs a type system, a type checker, to figure out whether they do. Okay, so a logical proof system is a way of formalizing what's provable, which may differ from what's actually true. Right? Maybe what your logical proof system lets you prove is not all true formulas. That would mean it's incomplete. Maybe, and this would be terrible, maybe it lets you prove some formulas that are false. In that case, it would be unsound. All right. There's two different ways that people have invented for writing down logical proof systems. And one of them you're familiar with actually already, because it's the way we did type systems. That's called a Gensen-style system. That's the name of a logician. A Gensen-style system has a lot of inference rules, just like we had a lot of type-checking rules. And maybe it has a few axioms, a few things that don't actually require any premises above the line. The opposite of that is called a Hilbert-style system, named for another logician, mathematician. This has a lot of axioms and very few inference rules. In fact, maybe the only inference rule is modus ponens. Okay, so remember that an inference rule, just like a type-checking rule, is a set of premises above a line and a conclusion below a line. And an inference rule is expressing what are the allowed means of doing reasoning. So this inference rule would say, if you have all of these assumptions, P1 through Pn, if you conclude all of those hold, then you're allowed to conclude that Q also holds. An axiom is just an inference rule with zero things. You don't need any assumptions. Okay. Now, in terms of drilling down into these individual P's and Q's, in our type system, those had a particular form of a ternary relation, right? So I'm going to call that ternary relation more generally today a judgment. It's a judgment about what you are allowed to conclude. So from these assumptions, A1 through AN, those show B. I'm allowed to conclude B. So before we had assumptions that were in the form of a static environment, assuming that like variable x has type int, variable y has type string, etc. And then we were allowed to conclude something over here on the right. For type systems, that was an expression has a given type, but in a logic, it might just be that some logical formula holds. Okay, so this is kind of judging the fact that B is derivable or provable. And it's doing it in particular by saying, if I had all of these assumptions and I knew those hold, these A1 through AN, then hypothetically speaking, if I had those, I would be able to conclude B. So that's a kind of hypothetical reasoning going on. If you had something on the left-hand side here, like suppose you hypothetically knew that A were true, then you'd be allowed to conclude that A, in fact, is true. That's the basic fundamental principle of hypothetical reasoning. If you can assume something, then from that you conclude that that same thing is true. Okay. So, with all of that in place, here are the inference rules that are used in formal logic in a Gensen-style system for implication and conjunction. So let's take a close look at each of these. And it's traditional here to write gamma for a set of assumptions and then comma to add another assumption onto it. So if from some set of assumptions gamma and an additional assumption A, you could show that B holds, then you're allowed to rewrite that to conclude that from that set of assumptions gamma, you can conclude A implies B. What this is saying is you can push an assumption from the left-hand side of that turnstile there to the right-hand side of it, and that introduces an implication. So the name of this rule is implication introduction, because the formula on the judgment on the top here did not have an implication. The judgment on the bottom does have an implication. We have introduced it with this rule. And the rule is basically saying, from a hypothetical kind of reasoning where, if A holds, I'm allowed to conclude B, then I'm allowed to change that into a logical formula that says the assumption of A therefore entails B. Okay, let's go to the top right here. Suppose we have two premises up here. From a set of assumptions gamma, somehow we can conclude A implies B, and from that same set of assumptions, we can conclude A. This rule says we can get rid of the implication and just leave that as gamma proves B. Why? Because A implies B is saying that if you could assume A, you're allowed to conclude B. And by the way, we also know that A does in fact hold, so it is valid to assume A. From that, we can get B out, therefore. Okay, and let's do the rules for conjunction now. Suppose that gamma proves A, gamma proves B, then gamma proves A and B at the same time, right? There's enough assumptions sitting around in gamma there to conclude that both of them hold. So that's called conjunction introduction, because there was no conjunction above the line. Now there is a conjunction below it. And for conjunction, we get two elimination rules. So if you know that gamma proves A and B, then you're allowed to eliminate that conjunction and just conclude that gamma proves A. And separately, as another inference rule, if you know A and B holds from gamma, then you know that B holds as well. So both of these are eliminating the conjunction, but there's two ways to eliminate it because you could either be left with A or you could be left with B. So one way of thinking about these inference rules is that they are how to define and use these like logical operators. Sometimes people call them logical connectives because they're ways of connecting formulas together. And the key insight that Gensen had a long time ago was that every operator should come with introduction and elimination rules to define how to introduce it into the bottom and how to eliminate it from the top. Okay, that's just a tiny, tiny bit of logic there. It's exactly enough that we needed to understand to go back and now look a little more closely at the typing rules that we had. Okay, so remember, we were talking about this function application typing rule. It says if you have E1 and it has type T arrow U, and if you have E2 that has type T, then the entire application has type U. Well, if I write that as an inference rule, as a proof rule, as we did in the recitation on typing systems, then what do I get? I get a premise here that says E1 has type T arrow U, a premise that says E2 has type T, and all in the same static environment, and the application of E1 to E2 has type U. Now, put on your goggles, erase all the programs, leaving just the types, and rewrite all of those function arrows as logical implication. And what you are left with is exactly the implication elimination rule. The rule that's used to define implication in logic is exactly the same as the rule that's used to type function application in programming. That's deeply surprising. What this is saying is that modus ponens, a reasoning principle discovered 2,000 years ago at least, if not longer, is actually function application, which is something that arguably was only discovered in the 20th century. They express the same underlying idea of being able to do a transformation. In logic, you're transforming this T arrow U by kind of giving it a T and getting out a U. In programming, you're taking a function, giving an input, and getting an output back. So one way to think about the program, therefore, is that you're doing computing on evidence. So what I mean by that is think about functions. We think about them as taking integers as inputs. We think about them as taking strings as inputs. What if we thought about functions as taking evidence as inputs? In fact, there's sort of a way of thinking about that already. If you have a function that's supposed to take an int as input, by passing, say, 42 to it, in a way you're providing evidence that there are values of type int. Right? 42 is a kind of evidence that there is a value of type int. And for basically all OCaml types, you could construct such evidence, but not for void, not for empty. You can't write down a value of that type. So in a way, when we have a type that a function takes in as input or produces as output, what we're doing is giving evidence that there is a value of that type. Modus ponens is doing kind of the same thing. It's taking in evidence for some logical proposition, that evidence here for T, and using that together with the fact that T implies U to get back evidence for U. So you can think of logical implication here as a kind of evidence transformer. Just like a function in functional programming is a kind of value transformer. It transforms one value into another value. So by doing that kind of application, that transformation of evidence or transformation of values, you can look at the expression E1, E2 as a program. It's the program that takes the expression E1 and applies it as a function to E2. And you can also look at it as a proof. It's a transformation of evidence for whatever E2 gives you into another kind of evidence. And that's what you do in proofs when you reason with implications. Okay, once more, the skeptic could say, well, all you've done this for really is implication. That's just a nice kind of cute little result, but it probably doesn't hold in general. That skeptic would be wrong. You can do this for all of the logical connectives, and people have been working on this for the last 30 years to show that, in fact, there's many, many, many kinds of logics, and all of them correspond to logics in the same way. I'll just do it for pairs here for now. So suppose these are the typing rules here for the first and the second functions on pairs. So if E has type T1 star T2, then you're allowed to conclude that first E has type T1. You're just taking that first component of the pair out, and the symmetric thing for second. Put on your goggles, and what do you get? You get the and elimination rules. The same rules that are used in logic to reason about how to break apart conjunction are exactly the same rules that are used in functional programming to break apart pairs. So we've got T1 and T2. From that, we can conclude T1. T1 and T2. From that, conclude T2. Again, you can think about this as computing with evidence. I suppose you've got a function. It takes in evidence, like combined evidence for T1 and T2. The first function, FST, transforms that evidence. It sort of drops the evidence for T2 on the floor, just leaving the evidence for T1. The function SND, second, does exactly the symmetric thing. It drops the first piece of evidence. So, to sort of summarize what's really going on here, if you have a well-typed program, as we said a minute ago, that demonstrates that there's at least one value for that type, that the type, there's a technical word for this, that the type is inhabited. A type is inhabited as long as there's at least one value of that type. So unit is inhabited, bool is inhabited, void or empty is not inhabited. A program is a proof that that type is inhabited, that there's at least one value of that type. And that proof demonstrates that there's at least one way of deriving the formula that the type of the program corresponds to. So when you write down a well-typed program, not only are you writing down implicitly a logical formula, which is the type of the program, and not only is that formula true, in fact, you are giving the proof of that formula. And that proof corresponds to the typing derivation in the type system that shows that that program is well typed. And so in that deep sense, programs are proofs, because every time you write down a program, you're actually writing down a proof. And proofs are programs, because you could take any proof of a logical proposition with those connectives and come up with a corresponding program for it. So programs and proofs are fundamentally the same idea. That's deeply surprising. But it's not all. And that brings us to Act 3. Evaluation is simplification of proofs. Okay. There are a lot of types out in the world. And for any given type, there could be many values of that type. Right? There are many values of type int. There are many values of type alpha list, etc. Also, there are many formulas out there in the world. And there are many proofs you could give for any given formula. Right? Suppose that you were asked to prove something on a 2800 problem set. There's 200 people in the class. Maybe there's 10, 20, 50 different ways that people come up with to do that proof. They're all proving the same thing. They've just come up with slightly different proofs. So a given proposition or type could have many proofs or programs. Here's a couple examples. So here's a logical proposition. Here's that same proposition read as a type. So we are going to pun the two of these things together. Here's a proof/program. You could think of it as being either one because they really are the same thing. Let's read it as a program. It's a program that has an anonymous function that takes in an argument x, returns an anonymous function that takes in an argument y, returns an anonymous function that takes in an argument z, and then does some complicated stuff here with x, y, and z. What does it do? Well, it takes z, constructs a pair, which is the second component of z followed by the first component of z, so it's just swapping the order of those components around. It's taking the pair and making the first the second and the second the first. And then we're applying that to the pair yx. Okay, so you all know how to do evaluation at this point. We've gone through a couple lectures on substitution model and environment model. Let's evaluate this in the substitution model. So if you take that as a program and take one step of evaluation, you're going to take yx here. That is going to become the argument z to this function. And when we substitute yx for z in here, we're going to take the second of yx and the first of yx. Normally we don't take steps of evaluation inside of function bodies. Right now I'm going to allow it. If we take another step of evaluation inside of the function body, well, second applied to yx gives us back x. First applied to yx gives us back y. So that gives us the pair x comma y. Now, if you look at all of those programs, they all have this type up here. And in fact, when we talked about type systems, that was a property we wanted. We wanted preservation as a property of a type system, if you remember. Taking a step of evaluation always preserves the type. The type never changes. Okay, so all of these programs have the same type. That type happens to correspond to that logical proposition. A implies B implies A and B. Now think about the typing derivation in terms of a proof tree that you would construct for each of these programs. So here you're going to have a fairly small proof tree because there's just not as many expressions involved in the program. Here you're going to have a bigger one because there's a lot more, like these seconds and firsts. And here you're going to have even bigger proof tree if you had it right down to prove what the type of the program is, because you've got another function application sitting there. So really big proof tree, smaller proof tree, smallest proof tree. Well, think about each of those programs as a proof then. So here's just the body of each of those functions. You sort of see it's getting simpler and simpler and simpler there. Each is a result of small stepping the program. In each case, the program gets simpler, and the corresponding proof that it's well typed gets simpler. In other words, you're giving a better proof, to the extent that a simpler proof, a smaller proof is better anyway, right? If you can write down a one-paragraph proof for your solution to a 2800 problem set versus someone who takes 3 pages to write it down, probably your one-paragraph version, as long as it's right, is a better version of that proof. Well, it's the same thing here. Every step of evaluation is making it simpler and smaller, and thereby making the proof a little bit better. So taking an evaluation step in a functional program corresponds to simplifying a logical proof. Simplification of an expression, simplification of a proof, those are fundamentally the same idea. Another deep, surprising result. Okay. Let me wrap up what we've said here today. These are all the same ideas. This is not obvious at first. In hindsight, it makes sense. Types and propositions are the same. Programs and proofs are the same. Evaluation and simplification are the same. So what I've talked about here today is a correspondence between functional programming and reasoning, logic. There is this deep connection between what you do here in 3110 and what you do to make arguments in the real world, to do 2800 problem sets, just to function as a human and do correct reasoning. So computation, seen as functional programming, really is, in a deep sense, the same thing as reasoning. And that's why, to go back to what I said at the beginning, that's why I view functional programming as so fundamental, something that is so interesting to study, because it really is just reasoning.